This is one of a series of revision lectures for A-level mathematics produced by the Further Maths Support Programme. In this particular lecture we're looking at the Edexcel Decision Maths 1 specification, and the topic for this one is linear programming. The specification says that you should be able to formulate problems as linear programs. So in other words, given a question in words, you need to be able to write out the set of equations that it produces in terms of what are called constraints. These would be, for example, if you have x and y as our variables, we may find that the 2x plus 3y is less than or equal to some value. So that will come out in the problem that we look at a little bit later. Well, having written down the constraints, we're expected then to solve the problems using a ruler and vertex method. Now this involves drawing the lines for the constraints onto a graph, xy graph, and indicating the region which is what's called the feasible region. Now what we do there is we shade out those values which are not allowed or not possible, remembering that x and y will be greater than 0, so we have constraints which says that y must be bigger than 0 and x must be bigger than 0. So we end up then with a region of the graph which is known as the feasible region. We use the convention that a solid line is used for points which are included in R. In other words, this would be regions which are less than or equal to or bigger than or equal to, would be a solid line. But if we want to show that the points on the line are not included in R, that would be things like less than or greater than, we use a dashed line. Within the question we'll then have some information which will allow us to draw what's called a profit line, and by considering that line we can then determine where the maximum profit or minimum cost, if we're looking at a cost sort of question, will occur. We do that by moving the profit line through the region and looking at which point that it reaches finally. So it's actually going to exit at one of the corners of the feasible, one of the vertices of the feasible region. So we can see it's moved past one of them already, and then coming up to the second one, and for this particular profit line the final one is going to be crossed, is the one that's just gone over there, which would be this point here on my diagram. Had we had a slightly different profit line, however, we can see that this time it's the point on the near the top of the region which is the final point to be exited. Now the fact that it is always going to be at one of the vertices gives an alternative method for finding the profit, and that is to look at each of the vertices in turn and determine the profit at each of those vertices and look for the maximum. However, there are questions where the solution must have integer values, and for those the vertices are not necessarily going to be integers, and so in those situations you must then consider points which are close to the exiting, what's called the exiting vertex. So we would look not just at that point there, but maybe ones which are close to it, which are integer values. Okay, I'll now look at an exam question, and those points will become a little bit clearer, I hope. Reading through this question first of all, it says we're in charge of buying new cupboards for a school laboratory, and the cupboards are available in two different sizes, standard and large. We have a maximum budget of £1,800, so this is one of the constraints, and standard cupboards are £150, large cupboards cost £300. It says we want to let X be the number of standard cupboards and Y the number of large cupboards. It's worth making sure that we've got that very clear. We know that X is standard and Y is large, and X cost £300. Beg your pardon, X costs £150 and Y costs £300. So the question then goes on and says write down an inequality in terms of X and Y to model this constraint. So that's one of the constraints that we're going to be looking at. We're then given a second constraint. The cupboards will be fitted to a wall 9 meters long. The standard cupboards are 90 centimeters and large cupboards are 120 centimeters. And we're asked to show that that constraint is modeled by a particular equation. Following that, we're also given a third constraint, y is greater than or equal to 2, and explain what this means. We have to explain what that means in the context of the question, so always referring back to what the question was about originally, not just treating it as an algebraic exercise. We then have another thing to consider, is that the capacity of a large cupboard is 40% greater than the capacity of the standard cupboard. And that's the thing that we want to maximize. So here our profit is the capacity of the cupboards. And we need to show that your objective can be expressed as maximizing 5x plus 7y. Well, working through those one at a time then, the first one is talking about the actual cost of these cupboards. So it says write down an inequality in terms of X and Y to model the cost. Well, if there are X standard, they cost £150 each, so that's 150X. The large ones cost £300 each, so 300Y, and that must be less than or equal to our total cost, 1,800. Now that would be sufficient to gain the marks. However, what we tend to do is to simplify this so that this means that X plus 2Y is less than or equal to 12. The second part is looking at the constraint involving the length. So I think we'll say that 9 meters is 900 centimeters, so that means that the length for all the x's are 90 centimeters each, so 90x, and the larger cupboards are 120, so 120y, and that must be less than the 900 centimeters that we have in total to fit along the wall. Well, that will divide by 30 throughout, so doing that, dividing by 30 is 3x plus 4y is less than or equal to 30, which is the constraint that we've been asked to find in the question. We have another constraint, y is greater than or equal to 2. We're asked to explain what this means in the context of the question. Well, y is the large cupboards, so this is saying that we must buy at least 2 of those, so at least 2 large cupboards. finally, this part of the question, we're told that the capacity of a large cupboard is 40% greater than the capacity of a standard. So if we let the capacity of the standard, so capacity of X, be C, then the capacity of the large ones will be equal to 1.4 times that, 40% bigger. So the total capacity is going to be C times X plus 1.4C multiplied by Y, the number of large cupboards. Well, we can therefore divide through by C, and if we also at the same time multiply up by 5, then what we need to do is to maximize (5x plus 7y). Well, before we move on to the graphing part of the question, just looking at how the marks were allocated for this. There was a method mark and an accuracy mark for that first constraint. You didn't actually need to do the simplification to get those marks. Again, a method and accuracy mark for the explanation of the showing the second constraint, and then B mark, so no method involved, just a statement of that last constraint in context, and finally a method and accuracy mark for the maximizing 5x plus 7y, the explanation of how that comes about. In the next part of the question, we're asked to represent all the inequalities graphically on axes in the answer booklet. So we're given a graph to put these onto. I've also included what are called the non-negativity constraints, the x and y. So we'll simply carefully mark in the fact that we must have positive values, so we're going to get rid of the negative part of the graph from here. So quite often those constraints get left out by students, so do be careful to make sure that you do include those. The other constraints that we've got are written up here. X plus 2y is less than or equal to 12, 3x plus 4y is less than or equal to 30, and then our profit 1. We also had the final constraint, y is greater than or equal to 2. The way to do these is to look at where do these lines cross the axis. So if we consider the equation x plus 2y is less than or equal to 12, the line equal to x plus 2y equals 12 will cross the x-axis at 12 and the y-axis at 6. So we're going to take a line joining those 2 points and marking it on a graph. Let's move it up slightly. So carefully done with a ruler, and then marking out again the region that we can't use, so we're going to mark out everything which is above that graph, and also label the line with this equation. So this one is x plus 2y is equal to 12. The second one, 3x plus 4y is less than or equal to 30. That will cross the x-axis at 10, and the y-axis at 7.5. And then finally the constraint that y is greater than or equal to 2. We're asked then to clearly indicate the feasible region. So the feasible region is this region inside the shading. For the final part of the question then, we're asked to find the number of standard cupboards and large cupboards need to be purchased, and we're trying to maximize, remember, the equation C is equal to 5x plus 7y. So one way to do that is to mark the line 5x plus 7y onto the graph. So one line which will fit that capacity equation is a line which crosses the x-axis at 7 and the y-axis at 5. Now that would be a particular capacity of 35. So this is a trick you can use. If you have any equation, we can multiply up the 5 by 7. So in this particular one, we're looking at 5x plus 7y is equal to 35. And that will give me one possibility for capacity. But we can do better than that by actually moving that line away from the origin through the feasible region, looking at the points that it crosses out of the feasible region. So it's just coming to the first point at the top left hand corner there, and then exits. This is actually very, very close. Both of these points here are quite close to each other, but I think we'll see that the final one that we go through is given by the intersection of the green and the yellow lines there. So what we now want to do is to say, well, okay, what value of x and y does that point where these intersect give us? So the point where the green and the yellow lines intersect, that's where 3x plus 4y is equal to 30, and x plus 2y is equal to 12. Well, we can solve these simultaneously, a and b. If I take equation A and subtract from it 2b, then that gives x is equal to 6. And substituting back in, if x is equal to 6, y is equal to 3. And that gives us our best option. Now that happens to be an integer value. However, sometimes the intersection point is not going to be an integer, but you require in your answer to have integers. Obviously we can't buy a fraction of numbers of cupboards. So if that's the case, you would, rather than just looking at that point, you would need to search for points close by, other integer possibilities. At the moment we've got 6, 3. Perhaps we'd need to look at 5, 3. Obviously if 6, 3 was outside the region, we'd be looking at points which were close by. The alternative method for finding the 6, 3 is to go through all of the points at the edge of the vertices of the feasible region. So not just the one that we found by using the line, but looking at all of these points which are at the edges and showing which one of those gives us a maximum capacity. Anyway, but whichever method you've used, you then need to write down a solution. So we need to say our best option is to buy 6 standard and 3 large cupboards. It's important that the answer to your question is put back in the context of the question. So it's not just a case of saying x equals 6 and y equals 3. It must go back into context. Looking at the marking for this question then, there were 3 marks, B marks, for each of the lines. There was another B mark, so no method involved, for correct shading. And a B mark for labels and using a ruler. Finally, there was a B mark for correctly identifying the feasible region. So that was the 6 marks available for the graph itself. In the final part of the question, 4 marks available. Depending how you did it, if you did it by a profit line, then M1, A1 for that profit line. Similarly, M1, A1 if the method you preferred was to look at all of the vertices. Finally, an A mark for getting x equal to 6 and y equal to 3. And another A mark for writing that in context. Well, that's the end of this lecture. However, you can find further lectures on the website, which is www.furthermaths.org.uk.